What if identity on the web worked less like repeated logins and more like trusted proof you carry? In this course, we'll build that intuition through issuing, holding, verifying, and protecting credentials with privacy designed in from the start. We'll move step by step. First, identity concepts, then the cryptography behind trust, then real credential flows, and finally, zero-knowledge privacy patterns. Plan for about 25 to 35 hours, depending on how deeply you work through the hands-on parts. The course is layered deliberately. We start with identity problems you already know from web systems: APIs, JWTs, access control, and back-end trust boundaries. From there, we introduce verifiable credentials and DIDs as a new trust model. Then the cryptography and zero-knowledge ideas have a clear purpose, instead of feeling abstract. Finally, we implement issuer, holder, and verifier services and use privacy architecture to disclose less data while preserving trust. Use your background strategically. If you're new to these topics, build the foundations in order. If you're experienced, you can move faster, but slow down for implementation, zero-knowledge proofs, and threat models. Throughout the course, keep asking, who is trusted? Where does the data flow? And what can each party actually verify? We begin by treating digital identity as a system, not just a login box. Identity describes who or what an entity is. Authentication proves it. Authorization decides what it can do. Trust explains why another party should believe a claim. We'll compare centralized accounts, federated providers, and decentralized models where credentials move through issuers, holders, and verifiers. This mental map gives us the language for every protocol, API, and design choice that follows. Keep these three ideas separate. Identity is the set of claims about an entity: age, license, role, or membership. Authentication is proof that someone controls a factor or key, so the system believes the presenter is present. Authorization is the policy decision that follows. What may this person do now? You can log in successfully and still be denied access. Verifiable credentials mainly reshape how identity claims are packaged and proven. In a typical web app, identity is spread across several moving parts. The login flow authenticates the person, then the system issues a session or token to carry that proof forward. The user database holds profile attributes and account state. Each request passes through middleware, an API gateway, or a back-end service where authorization is enforced. Roles and permissions decide what the user can do, but they are not the identity itself. Picture a site like acmejobs.com handling identity on its own. It stores emails, password hashes, names, roles, and verification status, then makes every trust decision locally. That feels simple at launch because one app controls everything. But as more apps and users appear, the same work repeats everywhere: password resets, MFA, breach response, fraud checks, and compliance. Identity becomes duplicated, fragmented, and harder to secure consistently. Federated identity changes where login is handled. Instead of managing every account directly, an app trusts an identity provider to authenticate the user and issue proof of identity or permissions. SSO is the user experience. Sign in once, use many apps. OAuth 2 delegates access, often through API access tokens. OpenID Connect builds on OAuth 2 to confirm who the user is. SAML is older, but still common for enterprise workforce SSOs. The trade-off is convenience and central control, balanced against provider dependency and careful trust configuration. Every identity system answers the same question: who do we trust? In a centralized model, the application trusts its own database and verification process. In federation, the application shifts trust to an identity provider that authenticates users and releases claims. Both models can work well, but they create bottlenecks: limited user control, dependence on provider policies and uptime, and disruptions when integrations fail. Trust becomes convenient, but also concentrated. The key shift with verifiable credentials is that credentials are no longer trapped inside one organization's database. A university, employer, or government can issue a trusted credential to a person's digital wallet. That person can reuse it across services, while verifiers check authenticity cryptographically, instead of calling the issuer each time. This improves interoperability, reduces lock-in, and supports privacy, because the holder can share only the specific claim needed, such as over 18, rather than a full identity record. Verifiable credentials separate the trust model into three jobs. An issuer creates a signed digital statement containing claims, metadata, and proof material. The holder stores it in a wallet and chooses when to present it. The verifier does not need to call the issuer for every interaction. Instead, it checks the cryptographic signature, status, expiration, schema, and whether the issuer is trusted. If those checks pass, the service can rely on the credential with much less friction. A useful way to see this is as a trust triangle. The issuer creates and signs a credential, like a DMV issuing a license or a university issuing a diploma. The holder receives it, stores it, and decides when to present it, usually from a digital wallet. The verifier asks for evidence and checks the proof before granting access or approval. These roles are contextual. The same organization may issue in one interaction and verify in another. Here's the pattern in practice. A trusted issuer creates a credential for age, membership, license, or certification status. The user holds it in their wallet and controls when it is shared. When a service needs eligibility, the user presents a proof, not necessarily the whole credential. The verifier checks that proof and grants or denies access. Later, zero-knowledge techniques make this even stronger. Prove over 18 without exposing the full birth date. You now have the map for this course. Identity, authentication, and authorization are connected, but distinct. Centralized and federated systems solve real problems, while creating important trade-offs. Verifiable credentials shift trust across issuer, holder, and verifier. Next, we'll inspect the building blocks, VCs and decentralized identifiers,